All right, so welcome back. Now we're going to be talking about the limit comparison test. And for this test, we have a pretty similar scenario to what we had in lecture 20 for the direct comparison test. So this test says, suppose you have two different series, just like before, and they're a series with positive terms. If the limit as n goes to infinity of a of n over b of n is equal to c, where c is a finite number and c is greater than 0, then either both of the two series, summation a of n and b of n, converge, or both of the two, so I'll just write it again, both of the series diverge. So what happens is they both have the same behavior. And just like the previous test, you're going to need to make a guess, and you're going to need to find the b of n that's the best to use. And when you make your guess is going to be based on which b of n did you pick. Did you pick a convergent thing, or did you pick a divergent thing? So in all those regards, it's the same kind of test as the previous test. So let's just take a look at this one. So you may recognize this from the last video. This is the problem we left off on because we couldn't use direct comparison test. But let's try using the limit comparison test now. So this is my a of n. And the b of n I tried using in the last video was 1 over the square root of n, which is 1 over n to the 1/2 power. And we know that this p series here, 1 over n to the 1/2 power, n equals 1 to infinity, this is a divergent p series. It's divergent because p is less than 1, less than or equal to 1. So the thing I've chosen is a divergent thing. So what that means is my guess is going to be that the thing I've started with is also going to be divergent. So that's my guess, because the thing I picked is divergent. So instead of doing some kind of inequality, we follow this formula. So for this test, you use a limit, hence limit comparison test. So you do the limit as n goes to infinity of a of n over b of n. So a of n is the original, the starting thing. So this is 1 over 1 plus square root of n. And I divide it by b of n, the choice that I've made, which is 1 over square root of n. I have a fraction divided by a fraction, so I'm just going to flip them. So this is going to be limit as n goes to infinity. I'll flip this one up, and it's going to be the square root of n. And this will be 1 plus. So basically, I did keep, change, flip. I did that fraction arithmetic. And now you have, if you try to evaluate n goes to infinity, you have infinity over infinity. So you could use L'Hopital's rule, which if you want to, you can take the derivative of the top and the bottom and then try again. I think that works out. But what I'm just going to notice is that the numerator and denominator have the same degree. They're both to the 1/2 power. So we take the ratio of the leading coefficients here, and that's just going to be 1 over 1. So this is our c. That's what it's saying in the statement. This is our c. And it is a finite number greater than 1. It's actually, it's greater than 1, it's finite. So what this means is as soon as you get this, you say this means by the limit comparison test, both summation a of n and summation b of n have the same behavior. But I know the behavior b sub n because I picked it that way. It's divergent. So this just tells me that both diverged. So I'm just going to say that this one diverges. And that's it. That's how you use the limit comparison test. If you want, you can try these three right now. See if you can come up with your own b sub n. I'm going to do them right now, but maybe you should try them and then come back. So here's this one. I'm going to call this a sub n. And for my b sub n, I'm going to choose 1 over 2 to the n, because I know that the summation of b sub n of this is a convergent geometric series. So this means that my guess is going to be that this is convergent. OK, so let's go ahead and compare that to this, which the only difference between this and this is there's this minus 1 in the denominator. But let's take this limit and see what happens. So I have 1 over 2 to the n minus 1 divided by 1 over 2 to the n. So this is my a of n over my b of n. I'm using my formula. Then I'm going to do keep, change, flip. So if I keep this fraction and flip the other one on top and multiply, I'm going to have 2 to the n over 2 to the n minus 1. Here I'm going to do a little bit of different arithmetic than I did over here to get the limit. So here I'm going to divide everything by the positive number 2 to the n. So I'm going to divide all three terms by that. So you're going to get 1 over. So divide all of these three terms by 2 to the n. And then if you divide the last one by 2 to the n, you get 1 over 2 to the n. So 1 and 1 are unaffected by the limit, but here I have 1 over, and this is going to be huge. It's going to be 2 to the infinity. So this fraction goes to 0, and I get 1. So that's indeed larger than 0. So I could say by the limit comparison test, both of the series, both of these, will do the same thing. And I know this one converges. So that means they both converge. OK, let me show you one like this where there's a bunch of n's and stuff going on here. So this would be very hard to do the direct comparison test, because I feel like there's a lot of different things going on. What you need to look at is, in the numerator denominator, look for the dominant terms. So these are the things that have the highest power that you see overall. And then that's what's going to be used for your b sub n. So on top, the highest power I see is at n squared. I'm going to take the whole term, too. It makes the math easier. So I have this whole term is the largest power. Down here, I have a excuse me, I have an n to the 5th. And then I have the square root. So in the denominator, my largest power is actually n to the 5 over 2 to account for that square root. And that's going to be my b sub n. And let me simplify that a little bit. So this is 2 over. 2 is 4 over 2, and this is 5 over 2. So these cancel, and you're left with 1 over 2 in the denominator. Now, this series, the summation of b sub n, this right here, this would diverge because it's a p series, and p is less than or equal to 1. P is actually a half this time, right? So I know this diverges. So that's my guess. We're going to diverge. And now let's take this limit. I think this might be the trickiest limit so far. So this is the limit as n goes to infinity of, this is my a sub n. So it's 2n squared plus 3n divided by the square root of 5 plus n to the 5th power, not squared. I think I took the 5 and flipped it around in my head. So that's a sub n. This would be over this one right here, which is 2 over n to the 1/2. And now let's do some algebra to figure this out. So we have the limit as n goes to infinity. I'm going to do keep, change, flip. So I'll keep the first fraction as it is. I'm going to change it to multiply, and then flip the other fraction, which is n to the 1/2 over 2. Now this n to the 1/2 will distribute across, and this 2 will just get multiplied. So I'm going to get the limit as n goes to infinity distribute the n to the 1/2, and I get 2n to the 5/2 plus 3n to the 3/2 over 2 square root of 5 plus n to the 5th. So now what I'm going to do is I'm going to multiply the top and the bottom by the highest power of n that I see. I'm going to introduce that as this factor right here. So this is going to be 1 over n to the 5 over 2 divided by, and then I'd like to be able to move this factor that I'm multiplying by on the inside. So I'm going to write this one as 1 over the square root of n to the 5. These are the same thing, right? Because if I take this 2 and I make it the square root, these are equivalent ways of writing the same thing. I'm just writing it like this because I can multiply this inside here. And then this one I'm just going to distribute. All right, I'm going to write out what that gives us now. So we're going to distribute this, and we're just going to get 2 plus this times this is 3 over n. If I subtract these, I have 2 over 2, which is n in the denominator, divided by 2. And then I'm going to be able to multiply this in because it's under the square root. So I get 5 over n to the 5th, and then plus 1. So this distributes into each of these. And now I'm going to go ahead and take the limit as n goes to infinity. So as n goes to infinity, this goes to 0 because you have infinity in the denominator, and this also goes to 0. Now if we collect what we have left here, I have 2 over, and I see the square root of 1 is here, times 2 is another 2. So this is 1, which is greater than 0. So it is finite. So this means that by the limit comparison test, both summation of A and summation of B do what? What did I pick? I picked something that diverged, right? So they both diverge. Algebra is a little tricky for that one, but we got there. OK, this one's interesting. So whenever you see a sine or you see a tangent, here's my advice. Ignore it, and then whatever's left over, any other terms, once you cover up the sine, all those together, that's what your b sub n is going to be. So if I cover up the sine, b sub n should be anything left over, which is the 1 over n. Well, we know that this would diverge. It's the harmonic series. So that means my guess is going to be diverge. So let's go ahead and attempt to do the limit comparison test. This is the limit as n goes to infinity of a sub n over b sub n. And remember, that's always my a sub n. So this is the limit as n goes to infinity. I have sine of 1 over n over 1 over n. Now this brings us to a special limit we learned in the beginning of Calculus 1. At least my class did. But this is a limit that comes out of Calculus 1. So you need to recall this. The limit as x goes to 0 of sine of x over x, that's 1. You could prove that using L'Hopital's rule if you wanted to, but this is 1. What's happening here? As n goes to infinity, we have the inside here goes to 0, and this goes to 0. So they're both going to 0. So what I'm going to do is I'm just going to make a substitution. I'm going to say, let x equal 1 over n. And then when you do that, we could say as x goes to 0, you have sine of x over x. Because I'm replacing the 1 over n's with x's. And then as n goes to infinity, in this expression, 1 over infinity goes to 0. So this is the same thing, and then I just get 1, which again is greater than 0, so it's c. So this series and b sub n have the same behavior. So by the limit comparison test, I picked a divergent thing, right? Yep. Both diverge. I'm a little confused on how much time I've already spent on this, so I'm going to regroup and then come back with some examples. I'll see you in just a second. So here we have 3 final examples, and I thought it'd be really good for us to review both direct comparison test and limit comparison test at the same time. So I'm telling you to try these on your own, and you could try limit comparison test or you could try direct comparison test. In my mind, one might work better than the other one. But try them out. See if you can use one of the tests to show whether these series converge or diverge. And then one little warning I'll give you is right here for the last one. This n here, exclamation mark, means n factorial. And what a factorial is it takes, starting from n, it takes the product of all the numbers from n all the way down to 1. OK, so give these a try. Come back when you're ready. I made these challenging just to, to really try to prepare you here. And I'm going to get started now. So with this first one, I see this 1 over 10 to the n thing here. And that looks very geometric to me. So what I'm going to do first is I'm going to think about this sine of n. This might be very familiar from your squeeze theorem days. So sine of n for n, I'm going to say n goes from 0 to infinity here. Sine is always between -1 and 1. So what that means is this numerator, if you add 1 to it, so I add 1 to just the center here, what is it between now if I've increased this by 1? Well, the left side gets increased to 0, and the right side gets increased to 2. So I know that the numerator is always less than or equal to 2. So here's what I'm going to try. I'm going to say b sub n is equal to 2 over 10 to the n. And we know this series b sub n, which is equal to 2 summation 1 over 10 to the n, we know this is a convergent geometric. I've just multiplied it by 2, but it's still a convergent geometric. And now watch this. So we have 1 plus sine of n over 10 to the n. That's less than or equal to 2 over 10 to the n, right? And that's my b sub n. So because this is true, I know that this numerator is less than or equal to 2. And I know this is my b sub n. So here I have a convergent, and now I'm less than something that's convergent. So by direct comparison test, we have that the original series converges. So I've shown that something that I started with is less than a convergent. OK, that was my idea for this one. This one took me a little longer. However, you can kind of do it in a similar way. So look at it like this. So here's my a sub n. Write it out like this. This is 1 plus 1 over n squared divided by e to the n, right? If I move this to the denominator, that's another way of writing that. And then I looked at that for a while, and I thought, OK, if I ignore just this complicated top part, what if I chose my b of n to be 1 over e to the n? Just like I had 1 over 10 to the n. This right here, this 1 over e, if my r is 1 over e, the absolute value of r is less than 1, just like 1 over 10 was. So this right here, my summation b of n, which is summation of 1 over e to the n, this is a convergent geometric series again, because my r is 1 over e, and that's definitely less than 1. So this is a convergent geometric. So that all that means is that my guess is that this one is going to be convergent as well. But this time I'm going to use the limit comparison test. So I'm going to do the limit as n goes to infinity. The formula is a sub n, which is this. This is my a sub n, divided by b sub n, which is this. Remember, this n, 1 to any power is 1, so I can write it like this, or I can write it like this. They're equivalent. And now I've got to do the algebra. So I'm going to keep the first one, keep the numerator, and this one. And then I'm going to do keep, change, and I'm going to flip the bottom one like that. So flip this over. Very nicely, the e to the n's cancel. And then is this limit something we can do? As n goes to infinity, 1 over n, I mentioned this a few times in this video, that goes to 0. So I got 1 squared is 1. that is a number, a finite number greater than 0. So this means both summation a of n and b sub n, they do the same thing, same behavior. They both converge, because my guess was that they converge. And this is by the limit comparison test. So that's what I had in mind. This last one, bear with me for a moment. So if n equals 1, let's look at a of n. So my a of n is 1 over n factorial. For my b of n, I'm going to leave that for now. I'm going to wait off. I'm going to hold that off for a second. So when n equals 1, this would be 1 over 1. And I'm going to do a few of these. And I'm going to do this to illustrate something for you so you believe me. I'm going to go up to 4 of them. I need 4 of them. So if I do 2, I get 1 over 2 times 1. Basically, I'm making a table for us. If you plug 3 into a sub n, factorial is 3 times 2 times 1. And if I plug in 4, I get 4 times 3 times 2 times 1. Now, my guess is going to be that this is convergent. And just like the other 2 examples, I'm going to choose a geometric series. So let's let b of n be 1 over 2 to the n. So the summation of b of n is the summation of 1 over 2 to the n. And that's geometric. It's convergent for the 3rd time now. So it converges. That's my guess. It's converging. If I plug in 1 here, I get 1 over 2. If I plug in 2, I get 2 2's on the bottom. If I plug in 3, I get 3 2's on the bottom. If I plug in 4, I get 4 2's on the bottom. There's a reason I'm doing this. If I'm going to use direct comparison test, I need to make sure that the thing I have here, if this converges, the original I'm looking for needs to be less. I need to be less than a convergent thing. So which way does the inequality go here? So when we start out with n equals 1, 1 is greater than a half. Here I have a half is greater than a fourth. So right now it's going the wrong way. And then here I have 1 over 6. I have to compare that to 1 over 8. So again, this is larger. However, as soon as we cross n equals 4, it flips. And the reason why, if you think about it, is you're always going to be multiplying by 2's. But there's going to be a lot more numbers over here that suddenly become greater than 2. Each one of these are going to be greater, and it's going to offset this one. So what I'm going to say is, for n greater than or equal to 4, 1 over n factorial is strictly less than 1 over 2 to the n. And if you remember the statement, I said things just need to be eventually less than. There needs to be some n, so at some point you're eventually less than b sub n for all n. So here's that point where for all n after that, you do have the setup that you need. So for this, we have that this is true. So by the direct comparison test, summation of n equals 1 to infinity of 1 over n factorial converges as well. Because at some point, at n equals 4, this is less than a convergent geometric series. OK, so those are those 3 examples. I hope those were challenging. I wanted to challenge you with those. In the next video, we're going to talk about yet another test. We are getting to the end of these tests. Next is going to be alternating series test. So I will see you in lecture 22 for that. Have a nice day.